So, with all this baggage history behind us in optics, I think it might be appropriate just review some of the high peaks of the subject, and because they're going to be very relevant to what I'm going to say today. I'm not beginning at the beginning because that is a long time ago in optics, but this might be a good place to start. This man is Snell, and this man is Descartes, and they both invented a law which in the West, in English-speaking countries, is called Snell's law, and Dutch countries also, I guess, and in France it's called Descartes' law. They both had a share in its invention. And it tells how light interacts with materials. So if light impinges on glass, it refracts and it changes the angle at which it travels. And this law, discovered centuries ago, is still the basis of optical design. People do ray tracing calculations to show how light passes through the lens in your camera and a microscope and so on and so forth. And that is the chief tool of design of optical instruments, still valid today. It's not an exact law because it doesn't tell you about some other things that happen. It has nothing to say about how much light is reflected from that surface. To know that, you have to have a deeper theory which tells you about the wave theory of light. So you know very well that if you have a glass object, it's also shiny. It does reflect about 5–10% of the light, and that's not part of Snell's law. Somebody else who made a contribution was Galileo. He didn't invent the telescope, but he made lenses so perfect that he could see things no man or woman had ever seen before. By the way, how many of you know that the word lens comes from this little bean called a lentil? And as you can see, it's lens-shaped. And that's where the name comes from. And with his telescope, Galileo could see things like the moons of Jupiter, which he named after his patrons, the Medici, or Florence. And we're going to be talking about focusing light. I mentioned that Snell's law was not a perfect law. It misses out several things, the wavelength nature of light being the chief one of them. And to understand light in much more detail, to the detail that we do today, we have to look inside the light and ask what it's composed of. And it's actually composed of electric and magnetic fields sustaining one another. And the road to our full understanding of light really began with this man, Maxwell Faraday. He worked in London at the Royal Institution. He was a very poor man when he started life. He had hardly any education, but he educated himself by going to the lectures of Humphrey Davy at the Royal Institution. And the lecture notes, which he wrote up very neatly, he bound up beautifully in leather. He was a bookbinder by trade, and he presented these to Humphrey Davy, who took him on as an assistant. And it was the best move ever made in science, I think, because he produced some wonderful things at the Royal Institution. I'll tell you about one of them, but there are actually dozens more things he did there in chemistry and physics. Now, Faraday discovered the laws of induction, and what he showed was that if you move a magnet through a coil, and it has to be moving, if it's stationary this doesn't happen, then a current will flow in that wire. So a magnetic field can produce an electric effect, and this was, we heard in the last two lectures about grand unification. This is the first unification of the electric and the magnetic fields to show that they were related. And Faraday had a particular way of thinking about magnetism. Now, in the days of Newton, when you talked about forces, you talked about action at a distance. When Newton announced his law of gravity. It was a force proportional to the mass of each object and inversely proportional to the square of the distance between them. And the interaction happened through empty space, through nothingness. Faraday didn't think about forces like that. When he was thinking about two magnets interacting, he thought of the first magnet, let's say, as being surrounded by a field which was there whether or not the second magnet was there. And he would say, well, if you don't believe me, he'd put a piece of paper over the magnet and he'll scatter iron filings on that. And those revealed to him his lines of magnetic force. And his law was stated not in direct mathematical terms, not in algebraic terms, but in geometrical terms. And he said that the voltage introduced into this coil by the motion was proportional to the rate at which these lines cut across the wire. And that, I'll spend a little bit of time on that because that was a very, very important step forward. Before that, this action at a distance idea prevailed, but this notion that a force was due to a field which was produced by the magnet but existed in space, well, it was a new notion. And the theory of fields is the theory which dominates modern particle physics. And here it is in its beginning. These fields are the first component of our understanding of light. Light is composed partly of these magnetic fields, which can produce an electric field if they change. Now, somebody else who also worked in London at King's College was James Clerk Maxwell. Very, very different background to Faraday. Faraday was the son of a poor man. Maxwell was son of a Scottish laird and was quite considerably wealthy, owned lands in Scotland. He was perhaps the most brilliant mathematician of his age, certainly in the United Kingdom. He died very young of, I think, stomach cancer at about age 49. And so, although he did many brilliant things and was of the same age as people like Kelvin, he's not nearly so well known and recognized as those scientists because he died well before the full flowering of what he did came to light, which was with Einstein in the 1900s. Now, Maxwell and Faraday were actually great friends. Maxwell was much younger than Faraday, and despite their backgrounds, they got on very well as men of science. And Maxwell wrote Faraday's law like this. So this symbol simply means the rate of change of the magnetic flux. That's the rate of cutting of these lines of magnetic force, the rate at which it cuts the wire. This is the cutting of the wire. The electric field is generated by a changing magnetic field. What the curly bits mean doesn't matter at this stage. But Maxwell recognized that these equations were incomplete, and he noticed anomalies when he tried to make them consistent. And he identified that what was missing from them was a symmetry. And the symmetry was that if you have an electric field created by a magnetic field, then you really do need to have a magnetic field created by an electric field. And D is just a version of writing the electric field. So these are Maxwell's equations, and they are the most complete description of electricity and magnetism short of the quantum theory. Now, Kelvin suggested to Maxwell that these equations should have a wave-like solution. And he, being a brilliant mathematician, very quickly found that there was indeed a wave-like solution. And the key thing was, what was the velocity of those waves? And at that time, this was before electricity and magnetism were united into one discipline, and there was a separate set of units for measuring magnetism and measuring electricity. And he had to find the ratio between those units, and he did an experiment which determined that ratio. And when he found that number, it was the known velocity of light. So before that time, people did not know what light consisted of. And Maxwell showed that light is a dance. It is a dance between the electric and the magnetic fields, the electric field changing into a magnetic field and back into a magnetic field. The step of the dance is the frequency, the step of the dance is the wavelength, and the beat of the dance is the frequency of the light. And so it was with these equations that we came to understand the inner nature of light. Now, you won't be surprised to see this man, and I'm sure I don't need to tell you his name. He is the icon of 20th century science. And the reason for that actually goes back to Maxwell. Because what Maxwell had shown was that if you go back to my statement about Faraday's ideas, Faraday liking to think of a force being exerted by a field rather than a magnet, then at that stage it was a theoretical argument, because who can say whether it's action at a distance or whether it's a force exerted by a field? But once you know that electricity and magnetism can make light, then if I take an electrical charge and I shake it, electrical charge is surrounded by the fields, Faraday would say, but how can I catch them? Well, if I shake the charge, it will emit light, and the light will carry the fields off with their accompanying magnetic field to a far distance, completely disconnected. You can send them to Mars, and the man on Mars won't know that they've been generated by you shaking a charge about here. All he will see will be the fields, and it was with this result of a wave that the reality of fields became established. But there was a problem, because up to that time, waves were always waves of something. So you have a water wave. What is it waving? It's waving water. You have sound, which is a wave in air. It's a vibration of air. But what is light? What is vibrating? So people agonized about this, and they came up with all sorts of theories about the luminiferous ether. And they were very uncomfortable, because this Newtonian idea of vacuum being nothingness, emptiness, was what prevailed. And the idea that it could be shaken about by something, by electric and magnetic fields, to make a wave was really quite astonishing. People had rather hoped, I think, that light could be shown to be some sort of particle, and then that would be something going through the ether, but it wasn't. It was a wave. And the story continued with Einstein, because what he showed was that not only could you have fields existing in this empty thing, the vacuum, but the vacuum itself had structure. Now, what do I mean by that? We know what we mean if we take a piece of solid, a crystal of salt, for example. You can look at it in an X-ray machine. You see the atoms are raised X, Y, and Z. That's not what I mean by structure. What Einstein meant by structure was the geometry. What is the distance between 2 points? How do you measure that? How do you measure it on the surface of a sphere? The way you measure it on the surface of a sphere is different from the way you measure it on a flat desk, because the sphere has curvature. And Einstein showed that space has structure, and that space could be altered by gravitational objects. So the sun has a gravitational field, pretty weak compared with a black hole, but it's there. And that's why the planets orbit around the sun, in Einstein's view. So Einstein, like Faraday, was taking a field view of the gravitational force that gravity exerted not by action at a distance, but by a field. And it's the very geometry of space which is being altered by this field that making the planets go in their orbits. Now, if you believe that, it has some consequences, because you might accept that massive objects are bent in a field. Yeah, okay, it's just another way of saying things. But what about massless objects? Newton's law says that the force between two objects is proportional to the product of their masses. But light has no mass. On the other hand, if you bend space, light travels through space, and so the path of light has to be affected by gravity. And Einstein predicted how much the trajectory of light from a distant star should be bent when it passes by the sun. And he suggested an experiment. And the experiment was to look at a star passing behind the sun and to see that it was in a slightly different place in the heavens from when the sun wasn't there. Of course, you can't do that whilst the sun's shining, so you have to wait for it to be eclipsed by the moon. And when that happens, there's still a lot of glare, but you can just about see a star vanishing behind the sun. And in 1919, Arthur Stanley Eddington mounted 2 expeditions to measure just that. One of them didn't work because there's cloud, but the second one yielded a result which agreed with Einstein's. And the whole scientific world exploded with the sensation of the fact that space was bent around the sun. Now it's routine, and people use the bending of light by massive objects in distant galaxies to actually look at stars which are behind the galaxy. There's sort of lensing effect of the light coming from behind the massive object. So there were 2 revolutions. One, the introduction of a field existing in nothingness, and then Einstein's statement that it wasn't nothingness after all, it was something which was structure, that you could play about with the geometry, sometimes you could bend the space. And those themes will all enter into what I have to say today and tomorrow. So there are 2 new concepts that I want to introduce. One of them is this concept of transformation optics. So the old optics is Snell's law. It is approximate. It deals with refraction, discrete interfaces. And by the way, in optics, we have a very limited range of material optics. So if we wanted to do something different from this, we'd have to search very hard for different materials. So that's the old optics, and it's been very successful. But what we want to do now is to use optics on a very small length scale. One thing we might want to do is to interface light with electronics. Optoelectronics, it's a name you've all heard, I'm sure. A problem. You've probably heard that companies like Intel are all the time trying to write finer and finer lines on silicon chips. And I don't know if you know the latest, I'm not sure what it is, but I think the smallest line width is about 20 nanometers. Probably, as I say, the limit's being beaten. But the point is that electrons travel on computer chips in wires which are much, much thinner than the wavelength of light. The wavelength of light is about 500 nanometers, roughly speaking, which is an order of magnitude greater than the electron wires on a chip. So it's a conversation between a mouse and an elephant. And an optical fiber, which is the equivalent of a wire on a chip, is even bigger. That's 50 microns across, which is 50,000 nanometers compared with 20 nanometers, 1,000 times greater. So we have a problem. And we want to control light on a length scale where Snell's law has absolutely nothing to say. Of course, Snell's law doesn't know about the wave-like nature of light. It doesn't know about the component electric and magnetic fields. And so we have to go to Maxwell's equations. But Snell's law has a huge advantage because it's very pictorial. You can see the rays of light. you could imagine them being refracted at the interface. So if you're a technician designing an instrument, you can think it all through in your head. I want the light to go this way and this way, so I need such and such a refractive index. You don't have to beetle around in a computer program with trial and error. You have a design procedure, and it's all based on this terribly visual picture. But if you have a field, a sort of messy thing that obeys a bunch of equations, which takes lines and lines to write down, how do you control that? And that's what transformation optics is about. So we're going to go beyond the ray approximation. We want to go into what's called near-field optics, which is inside the wavelength, and manipulate the individual fields as well as the rays, and do the sub-wavelength optics. And also, we want to use, to do this, these new materials called metamaterials, which I'll come to later in my lecture. So with that rather long preamble, let me get down to the title that I've given you. Now, why am I talking about invisibility? And the reason is that we have this very powerful technique of transformation optics. We have these new materials called metamaterials, which I'll come to in a moment. And we wanted to show the world at large why we were so excited. What can we do that you couldn't do before? And it's all very well, you know, talking to a sophisticated audience like yourselves, showing a few equations and talking about fields and Einstein and so on. But the general public will quickly turn to the racing page if that's what you say to them. So we wanted to smack people between the eyes. And we thought of the most sensational thing we could do, and that was to make something invisible. That's only one thing that transformation optics can do, but it's the one which the general public will get hold of. And thanks to Harry Potter, they did in spades. But I'm not a Harry Potter fan, I'm a Peter Pan fan. Here is his statue, which sits in Kensington Gardens, just outside my college. And the first point I want to make about invisibility is that it's not enough to paint something black to make it invisible. Do we have some water, by the way? I'm very grateful. Because if you have a bright environment, something black is very visible. In fact, there are some sports like squash which are played with a black ball, but they're played in a very bright, usually white squash court, and the ball is certainly not invisible. So what we have to do is to make Peter lose his shadow, which is what he did, of course. Do you know the story? Peter Pan's shadow. And when Peter's shadow is gone, then he really is truly invisible. And by the way, just note that we don't have to do a fantastically good job if you're walking across Kensington Gardens, bleary-eyed at 9 o'clock in the morning, to lecture your students. You wouldn't notice Peter hiding in the trees, even though he's 50% there, I think. Anyway, so how do we do that? How do we lose the shadow? Well, it's been a problem that people have messed around with over the ages. This was H.G. Wells's solution. H.G. Wells, student at my college, he hated the place apparently. His mistake was to study physics, I suppose. And he wrote a book called The Invisible Man. And his solution was very simple. He just said, well, the invisible man will drink this chemical portion, and it will change the chemistry of his body, so his refractive index is 1, the same as the surrounding air, pretty much. So light passes straight through him in a straight line, not refracting at all. These days, health and safety wouldn't allow you such radical chemistry, so we'd have to think of another solution. And here's a more sophisticated version of that. And here we've introduced the concept of a cloak. So here's the object you want to hide, and now it's got a high refractive index. So if this wasn't cloaked, this will be scattering light off like mad in all directions. And so what we do is wrap around it a cloak which compensates for the refraction of this object here. You see, if the light goes in this fantastical path here, then it actually comes out headed in the same straight line as it would have done had none of this been present. So that's certainly possible, but if you change, you can't sort of muck about in here, because if you move around in here, the cloak has to move as well to compensate for you. And also, there are other technical problems to do with dependence on frequency and so on. So although that's a sophisticated solution, it's not quite sophisticated enough. And here's our preferred solution. This is going to deviate light so that when it hits this cloaking material here, it's steered away from this hidden region, but just as in the previous case, it's actually returned to the same path that it was on before it hit the cloak. And so an observer here would just see what was behind the cloak. It wouldn't see the cloak. It wouldn't see what was inside the cloak. As you can see, none of this light actually reaches inside here. So one drawback of this method is that if you're inside the cloak, you can't see out. But of course, that's an inevitable price, because there's something called the reciprocity theorem, that if I can see you, you can see me. Now, what's required here is some continuous bending of the light. So that's not really what Snell would have thought of. Snell was thinking of refraction at an interface. But there are instances in nature where light is bent continuously rather than suddenly at an interface. And one of them occurs in a mirage. So you all know what a mirage is, just to remind you. Typically, it might be in the desert. Hot sun heats the desert surface, and the desert surface in turn produces a layer of hot air just above the surface. Hot, less dense, and therefore less refractive. And this variation in the refractive index bends like this way, and if the effect's strong enough, the light from the sky can be bent up so that an observer would see the sky reflected in the desert surface. Reflections in desert surface must be an oasis, so it fools the poor, thirsty traveler into thinking that there's water there. I guess Australia is hot enough for this. In my country, we only see it in the summer on hot asphalt roads. So in the distance, you might see the road shimmering, and that's the mirage effect. You think it's wet, but it's not. When you get there, it's a perfectly hot, dry road. So we're going to do this continuous miraging thing. But now the problem is, yes, we know how to bend light in a continuous curve, but what curve and what gradient of the refractive index do we need to achieve this? We need a design strategy. And that's where transformation optics comes in. And here we start talking about things which would be familiar to Einstein. So this is the way I think of transformation optics. Suppose you have, let's say, a ray of light, or it might be a magnetic line of force or an electric line of force. Let's suppose it's a ray of light. And it's going in a straight line through space, as rays of light do. And I imagine that it's nailed or glued to a rubber sheet. And I'm going to impose the restriction on myself. If I want to alter the trajectory of that light, I'm going to pull this sheet, okay? So I'm going to imagine that the space in which it's embedded is like rubber. So I can distort the space. I've got a convenient black hole close by which would pull and toss in space. So when I'm done rearranging my black holes around here, the light is traveling in the direction I want. And that distortion I can record if, in the first instance, I've drawn a nice set of Cartesian coordinates on the rubber so that when I've distorted it, I can tell just how much I've distorted it. Now, one thing I didn't mention when I talked about Einstein's result, well, two things I didn't mention. One, that when Einstein said that gravity distorts space, the way he described that was through something called the metric, symbol G, wholly a symbol in general relativity. And the metric is quite simple to understand in concept. What it describes is just how much the gravitational field has compressed or stretched the space. And if you rewrite Maxwell's equations as Einstein did, using his formalism in a bent geometry, what you find is that metric comes in a very special place in Maxwell's equation. It comes in exactly the same place that the refractive index does. So the metric, as far as light is concerned, behaves like a refractive index. And that's why the sun acts like a very weak lens and bends starlight. It's got a refractive index around it due to its gravity. So fortunately, to do this, we don't have to shove over a few black holes around. We just have to make an arrangement of the refractive index. Einstein also was very helpful in that he said that if you want to know what metric translates into refractive index will do this job, then he can tell you the value of that in terms of the coordinate transformation. And it's a very simple formula involving the first derivatives of this coordinate transformation. So we can treat space as rubber and rearrange the light rays sitting on it. And when we're done, we can actually say, please, Mr. Einstein, these are the values in the formula. Tell us what refractive index we need to have light travel on this trajectory. So here's the design methodology for a cloak. First of all, I take a beam of light, and I want to make this inner region invisible. And then I say that I'm going to distort the surrounding space in a region which is going to be contained within some bigger, let's say, sphere. It could be any shape, but I choose a sphere. And the way I do that is sorry, that's your issues, isn't it? I stick my finger in space, and I tear a hole, and then I push on that hole, and so the contents of this inner sphere are pushed until they're contained between the boundary of the inner sphere and another bounding sphere here. So all the distortion is confined into an annulus between the two. And therefore, because we're not distorting space outside that annulus, these rays are totally undisturbed. But the rays in between never enter this region here because you've pushed out all the space. There's no space in there, it's empty. And the light goes on a trajectory which must return to its original path because there's no way that can be disturbed. And when you find the formula for that, so here we go. We have, here's my coordinate system. I make a hole. I compress in the radial direction. For those of you who like algebraic formulae, this is the coordinate transformation. The r prime coordinates are compressed by this factor here. And with this, from this transformation, you can find, here's the formula that Einstein might have used. Using the first derivatives, you can find what values of the permittivity and permeability, the electrical and magnetic response, which go to make the refractive index, how they change, and so what refractive index you must use there. Don't worry if the formula seems a bit confusing. All that's necessary to know is that there is a formula, and it's relatively simple to implement. So if we do that for a cloak, then the electrical, the refractive index, which is essentially this quantity here, actually it depends which way the light is traveling. If the light is traveling in a radial direction, you see this distortion is, this distortion is asymmetric. What started off as little squares here end up as rectangles. So you compress it in the radial direction, but you actually stretch it in the angular direction. So at the end of the day, you find that the refractive index for light heading in a radial direction is greater than 1, and the light heading around the radius has a refractive index of less than 1. So, but the main point is that you can calculate it, but how the hell can you build it? So how do you make a material which is changing its refractive index as you go? And that's where metamaterials come in. Again, the concept is a simple but powerful one. So ordinary materials like glass or water, they respond to light through the electrical field of light. The electrical field polarizes the molecules in the water or the glass, and that polarization affects the way light propagates. And despite the fact that all the molecules are randomly arranged in glass and water, if you average over the billions of them that are in 1 cubic wavelength, then their response is pretty uniform and consistent. And so you have a well-defined response to light. But the entities you're polarizing need not be as small as a molecule. They could be bigger. There could be something that you could actually make on a machine. And this is particularly true if you're working not with light, but with radar waves, which are also a form of light, but which have a much longer wavelength. And it's how many of these little cells you can fit inside a wavelength so that the wave doesn't see the details of them, it just sees the average response. And for example, you might make little metallic rings. That's one structure that we've looked at. And this concept of making function through structure is the whole idea behind a metamaterial. So a metamaterial's properties are derived more from its structure than from its composition. And the example I give is, for example, if you take a nice shiny silver surface, a flat silver surface, very reflecting to light. It's one of the most reflecting materials there is. But some of you may remember the old black and white photographs in your granny's drawer. They were made from silver halide, and the blackness is in fact due to silver. But the silver in the photograph is different from the silver in the mirror, only in that it has a different structure. The silver in the photograph comes in the form of little spherical balls, and when you make silver into lots of little particles like that, it turns very, very black instead of being very reflecting. And so that's an example of you radically altering the response of something by changing its structure. Here are some examples of metamaterials. This is one which we looked at very early. So instead of taking solid copper or gold, you could split dilute it, if you like, and make the metal into very thin wires. And then actually that does something to the motion of the electron, because when an electric current flows along this wire, it has not only to accelerate itself along, but remember, an electric current produces a magnetic field, and that takes energy. So you actually have to put in a lot more energy into a thin wire than a thick wire, because it's very inductive. And that makes the electrons very heavy. If you make very thin wires, a micron or so across, then the electron becomes as heavy as a nitrogen atom. And so that very much changes the response of this structure, and you can engineer the electrical response as a function of frequency very easily by altering the precise structure of this wire mesh. That's one structure which has an electrical response. Here's a structure which has a magnetic response. So what we have here is a ring of metal, and if you remember Faraday's laws, if we put a magnetic field on that ring, it will try to induce a current which flows round the ring. Now, if you had a complete ring, like a wedding ring, then the current would flow, and the current itself would produce a magnetic field. So here's a structure which has no intrinsically magnetic material in it, but has a magnetic response which it produces through electrical currents in a conductor. And this particular one has a little cut in it, so you make a resonance structure here, and that can do interesting things, which I will come to in the next lecture. And so the very first example of these metamaterials were made by Mark Wiltshire at Marconi, and this was designed to work with radar waves because that's what they were interested in. And the dimensions here are about 5 or 10 millimeters, little copper rings, and this has a very strong response to radar waves. But unlike most materials, it acts on the magnetic component of the radar wave, and therefore has certain useful properties. Now, another structure which has also become quite famous was made by David Smith using these principles. And in fact, you combine the two structures. Here are the little rings, and perhaps you can see a wire there, shadow of a wire on the other side of the board, assembled into this sort of egg shell structure. And this one actually turns out to have a negative refractive index. It was the first material ever made to have a refractive index which was negative. And again, I'll come to that in my next lecture. So these are the sorts of materials that we use to build the cloak according to the transformation optics formula. And only these materials can engineer the precise geometry that you need. And using them, you can steer light around an object like that. The experiment doesn't look quite so beautiful, but because it was designed for radar waves, and again, it was David Smith's team that built this. So here's the little rings, the metamaterial. This is producing a certain magnetic response, and that is graded as a function of the radius, because we want the refractive index to change as a function of the radius. And here's how the structure changes as a function of the radius to achieve this gradient. Now, okay, this is just a detail of the little cells that go into the metamaterial. Here's the experiment, which was for radar waves again. It was in a waveguide, so the fields are confined between two heavy aluminum sheets, two-dimensional experiment. Here's the cloak, there's the hidden region, and this gunk here is all radar-absorbing material, so no spurious signals that can observe. And we're going to map the fields out as radar waves hit this cloak and see if we can hide things. So this is a busy slide, but what we have here is a computer simulation of the wave field given the ideal parameters of the cloak. So here are the waves coming in. When they hit the cloak, they interact very, very strongly with it, but you can see the waves are being grabbed by the cloak and steered around. Here is what we call the pointing vector, which you can read as where the rays of light will go, and that shows you how they're steered around. So that's the perfect situation. A computer simulation shows that the theory works. Now, unfortunately, it was difficult to build the experiment precisely like this. Theorists are always asking experimenters to do impossible things. And the nearest they could get was these parameters here. This is a simulation of what the experiment should look like. And, well, okay, what you'd see here, you can see that this intensity coming through is not quite as strong here. So instead of something being invisible, you'd see sort of a gray disk in the sky, because you're absorbing some of the light here. Here's the experiment when you just have a bare cylinder of copper scattered all over the place. And now, if you introduce the cloak, you can see that the cloak is doing a very good job compared with the simulation. And it was thought at the time there had been certain mathematical theorems touted which said that it was impossible to hide something completely. So that when we published this experiment, it wasn't quite the treatment Einstein got, needless to say, but the New York Times were quite interested. I was speaking at a conference in Rochester on the day this appeared, and I didn't know it was appearing, and people were waving papers at me from the audience, and I thought they were telling me to shut up, but they were really, really telling me I was in the New York Times. So that was the very first thing, and well, it's hardly Harry Potter stuff, is it? But it certainly made an impact. What people have been doing since then is working towards making, if you like, a real cloak, pushing up the frequency up into the optical region. And to help that process, one of my postdocs, Jensen Lee, came up with the following idea. There are actually 3 ways that you can implement this procedure for a cloak. I told you one of them, which was to make a hole in space, starting from a point, and then push out all the stuff into an annulus, a sphere. Another way, you can start from a very, very thin line, and you can push out from that and push all the rubber material into a cylindrical annulus. There's a third way. Well, both those are invisible, because what it looks like is as if you squash the content of the sphere to a point. And it doesn't matter what the refractive index of the point is, it never scatters radiation. Likewise, if you squash material into a wire, which is what you started from, a very thin wire doesn't scatter radiation either. But the third way, which is to compress the material into a thin sheet, is, even if the thing's flattened, you can still see it, because if something's very, very refracting and it's in a thin sheet, it makes a mirror. Think of Bako foil, aluminium cooking foil. That's very, very thin, but it's still scattering like mad. Now, there's one way, however, you can hide something that's very, very thin, and that's to put it on a solid mirror. So if I put a mirror on a mirror, it still looks like a mirror, and you don't know that the second mirror is there. You get me? So we call this hiding under the carpet, because if you have an object which is really, first of all, you start with a flat mirror and then you make a little tent there, then you can obviously see that the mirror's got a bent in it. But if you put a cloak around it, it appears to squash that thing down so it's flat with the mirror, then you just think it's the mirror and nothing else. So we call this a carpet cloak. And it turns out that this geometrical procession for 3 dimensions, 2 dimension to 1 dimensional cloak, each one is successively easier to make. And it turns out that these optical cloaks are really sufficiently easy to make that you can do them at optical frequencies. So here was the first design by Jensen Lee. This chart here shows that you have a very high refractive index in this region, tailing off to smaller refractive indices as you go to the sides of this cloaking box, which is hiding this thing here. And the whole purpose of this cloak is to make this lump flat. So how well does that work? Well, the computer thinks it works pretty well. So if you have a lump here and you haven't screened it, then the 2 facets create 2 reflections instead of 1. But if you put the cloak over it, then you see a single reflection here. And people jumped on that, and the thing was actually manufactured in Jiang Zhang's group at the University of California, Berkeley. So I should point out this is really, really very tiny here. Do I have a scale on this? It's just a few microns across, so you could hardly see this with the naked eye. But what we have here is a cloaking region, and this is the simplest metamaterial possible. They reduce the refractive index of silicon just by drilling holes in it. And the more holes you drill in it, the less the refractive index. And here's the hidden region. That's a sketch of it, and here's an electron micrograph of what they actually made. So there's the cloaked region, here's the surrounding region, there's the hidden bit. And here are the experiments compared with the theory. So here are the data, and you can see that if you have a flat mirror, you just see 1 reflection. If you shine it off a bump, then you get several reflections from the facets of the bump. And if you put the cloak into place, you're back to the flat mirror again. So that was rather nice evidence that it worked. But, you know, this is about 10 or 20 microns across. God help me, what use is that? And it turns out that a group of guys who were working with Zhang's team, Xuanzang rather than Zhangzang, they got in touch with some guys in China who's had amazingly large crystals of calcite. And this is an anisotropic material with strange refractive index properties. And they figured a way of rejigging this carpet cloak so it could be made out of these calcite crystals. And they're really big. Well, centimeters rather than microns. So here's the deal. You now, instead of this thing being microns across, it's a few centimeters across. And again, you start with a flat surface, and you compress all this stuff up here. But now you're very careful to do it uniformly, because the calcite, although it's anisotropic, is homogeneous. And so you compress this uniformly, and you do it in such a way that you can actually get a calcite crystal in there, and all these angles are carefully calculated. And so this should appear to be exactly like that. Does it? Well, here's ray tracing. And this is what you get, the two facets producing two beams again. You put the cloak in place, and you get a single beam. So Ray says it should work. And what they did was to put the alphabet behind the cloak. And if you have no cloak there, you can see the alphabet scrambled up, not in the right order. There was a discontinuity in the middle. But if you then put the cloak in place, G, H, I, J, K, L, the alphabet is restored, and you don't see the join, as it were. So that was proof of concept. And for us, the whole point of it was not so much that you can hide a bit of rubbish over a 2-centimeter cloak. It was the principle of the thing. First of all, that you could design the cloak mathematically. You had a prescription for doing it, which was precise, accurate. And then you could actually make the thing using exotic materials, which often need to use metamaterials. On my next lecture, I'm going to talk about even more exotic things, which are things with a negative refractive index. And if you remember my statement that Einstein's metric, which is a measure of how much you squash space, could be identified with a refractive index, and the refractive index can go negative, what is the meaning of negative space? So I'll leave you to puzzle that. I'll tell you a little more about it tomorrow. Thank you.